Hello, my name is Victor Carl Chan, and I'm a PhD candidate at the University of Toronto, and I work in the field of cosmology, which studies the origin and evolution of the universe. And my work in particular spans all the way from studying the residual light of the Big Bang, all the way to the stars that are really close to us in order to study where we come from and where do we go. The Hubble constant is actually a very important parameter in cosmology because it relates very deeply with the age of the universe. One of the ways to measure the Hubble constant is through a method which we call the distance ladder. We can measure the distances to faraway objects in space, which isn't trivial, but can be done. And then we also tie them together with their apparent motions relative to us. If we take our measurements of the distances to these faraway galaxies and plot them against their recessional velocities, then the slope of the line that connects the points is actually the Hubble constant. Since these objects are moving away from us now, if we turn back time, they must have been closer together at some point. And if we turn back time far enough, we can infer that they were packed so closely together that they could have been touching. This tells us that there must have been a hot Big Bang at the origin of our universe. The residual light from the Big Bang when it reaches us is what we call the cosmic microwave background, and it presents us with a different opportunity to measure the Hubble constant. The cosmic microwave background, or CMB for short, is actually quite smooth at first glance. But on closer inspection, there are actually tiny fluctuations in what we call the temperature of the CMB. These temperature fluctuations come in all sorts of shapes and sizes. The sizes and shapes of the hot and cold spots in the CMB tell us about the overdensities and underdensities of gas in the early universe. These go on to evolve into the structures that we know today as galaxies and galaxy clusters. Through running many simulations of different models of what we expect to see back then and now, we can actually infer what the Hubble constant must be from what we observe in the CMB. To summarize, the Hubble constant is a very important cosmological parameter that tells us about the age of the universe. One way we can measure it is through the distance ladder, which maps out the recessional velocities of faraway galaxies. Another way is through the cosmic microwave background, where we can infer what it should be based on the hot and cold spots in the cosmic microwave background. Let's start with a little history. In the 1920s, Georges Lemaitre and Edwin Hubble used the distance ladder technique to measure the Hubble constant. This Hubble constant actually inferred the universe to be quite young. Ever since, we've been refining techniques with the distance ladder to get a better and better estimate of the Hubble constant. Nowadays, through measurements of the distance ladder, we think the universe is quite a lot older than what Lemaitre and Hubble thought. Fast forward a little bit to 2003. A satellite called WMAP observed the CMB in quite high definition, and cosmologists used its data to infer the Hubble constant once again. This time, it quite agreed with distance ladder measurements, but its uncertainties were quite high. Later on in 2013, another satellite called Planck measured the CMB in even more detail, but this time, the Hubble constant was inferred to be something different with quite high precision. So the Hubble tension is the disagreement in the measured Hubble constant through the distance ladder and the CMB. And it's very interesting because we don't really know why they disagree with each other. I expect that scientists' initial reactions would have been despair when things don't agree with each other. But when we take a step back, it's actually quite exciting when things don't agree because it means that there's something we could learn. I recently attended a conference about just the Hubble tension, and it was really funny because I expected scientists from all over the world to have gathered and intensely defend their ideas against each other. Instead, it was actually quite fun, and we had a lot of fun, proposing ideas for solutions to the Hubble tension and, just trying to understand what this could be. One of the more exciting solutions to the Hubble tension is to invoke new physics that would cause different Hubble constants to be measured from the early universe to the late universe. This includes models such as exotic dark matter and even evolving dark energy. These models are very fun, but it just so happens that the universe's evolution is quite complex. And once you start to tinker with one part of the universe, it tends to break another. This makes it quite hard to invoke new physics into our existing model of cosmology. One other way to tackle the Hubble tension is to simply take a step back and think, do we really trust our measurements? it really could just be observational error that leads to these discrepancies. If we don't trust our observations, maybe we can try new methods. And we can use other astrophysical phenomena such as quasar lensing, FRBs, and even gravitational waves to measure the Hubble constant. These methods are quite new, so they don't quite offer us precise measurements of the Hubble constant right now, but in the future, they're a great avenue to learn more about the Hubble tension. One of the biggest questions about the universe is, where do we come from and where will we go? And the field of cosmology is doing a lot to answer these questions. The fact that we've measured the Hubble constant so well tells us that we've learned quite a lot in order to help answer these questions. But the fact that they disagree tells us that we have a lot left to learn.